Hello, and for the last time, welcome back to Calculus. After 37 parts, we have finally arrived at the last video of the series to go over some examples of the Maclaurin series. I endlessly thank all the nice people that supported me and this channel by liking and subscribing, which made it possible for me to make more videos for you to enjoy. So without further ado, let's get into it. Now, please recall a quick recap from the last video. This here we have the formula for the Maclaurin series of any function, and we're able to write it in a more compact way using the sigma notation of k equals to 0 until n of f to the kth derivative evaluated at 0 divided by k factorial and times x raised to the power of k. So let's immediately construct the first Maclaurin series, and we will take the function f of x equals to e to the power of x, which is probably one of the simplest because the derivative does not change. So all of the derivatives are always e to the power of x, and when you plug in 0, you will always get 1. So let's say we are constructing the Maclaurin series of degree 6. Well, this would simply mean that e to the power of x can be written as a polynomial, specifically f of 0, 1 plus 1 divided by 1 times x plus 1 divided by 2 factorial times x squared plus 1 divided by 3 factorial x cubed, and so on. We're able to write this in a more prettier fashion, so 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial plus x5 over 5 factorial, and the last term 6 over 6 factorial. We could keep this going, but let's just say we stop here for now. Well, this wasn't very difficult, so let's do this again for a trigonometric function, specifically the cosine function. Now let's first find the first 5 derivatives of the cosine function. Now we know that the derivative of cosine is negative sine, then negative cosine, then back to sine, then back all the way to cosine, and this cycle will repeat itself. And now all I have to do is evaluate each derivative at 0. Of course, let's not forget the original function also needs to be evaluated at 0. So here, cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, then it's 0 again, then it's 1, then it's 0. So here, you might notice that some of the coefficients are going to be 0, so that means cosine technically is going to skip some terms. Now, if I were to construct the Maclaurin series for cosine of x, what I would get is 1 plus 0 divided by 1 times x. So technically the x term does not exist. So the next term is going to be negative 1 divided by 2 factorial times x squared. Following that, we have again 0 over 3 factorial x to the power of 3. So that means the third power of x vanishes. And the next one is going to be 1 over 4 factorial times x to the power of 4. And you might see the pattern emerging here. We have a little alternating polynomial, and the power matches what we're dividing it by of the factorial. We could continue this polynomial, however, I'm going to end it to the power of 6, and I'm going to show you the visualization of this Maclaurin series compared to the actual cosine curve. This graph here in orange would be the actual cosine wave between the values of negative 3 until 3. And this line in red would be the Maclaurin series that we just got. You can see they basically replicate each other, except here maybe at the endpoints they split off a little. However, this will fix itself if we add more and more terms to our Maclaurin series. Now I can also tell you immediately that if you remember the Maclaurin series for the cosine function, you will most definitely remember it for the sine function, because here you realize that the cosine Maclaurin series incorporates all x's with even powers. This one right here means x is raised to the power of 0. The sine function is going to be the opposite. It's going to incorporate all of the x's with the odd powers and skip all of the even powers. So what I mean is that sine of x is approximately equal to x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial and minus x to the power of 7 over 7 factorial, and you can already see the pattern and it's going to repeat itself endlessly. So these three Maclaurin series, sine, cosine, and e to the power of x are probably the most common and most useful to know. Also the one that we discussed in the last video, the natural log of 1 plus x. To end the video and also end the series, I'm going to present you a formula which can be used to construct the Maclaurin series for functions in a form of 1 plus x raised to the power of p, and it is called the binomial series. It simply says if you have a function in the form of 1 plus x raised to the power of p, the Maclaurin series for this binomial expansion would be 1 plus p times x plus p times p minus 1 divided by 2 factorial times x squared. And the general term in the expansion would be p times p minus 1 times p minus 2 and so on until p minus n plus 1 over n factorial times x raised to the power of n. Another way that this can be written is using the sigma notation from n equals to 0 until p of combination pn. Now please recall this parentheses right here is not what you think. It is the combination CNR, well, or in our case that would be combination pn or p select n. And this multiplied by x raised to the power of n. Now, I'm not going to tell you where this formula comes from. I'm going to challenge you to do what we did in the last video and arrive at this formula beginning with our function 1 plus x raised to the power of p. Just as a head start and a hint, I'm going to tell you that f of x is 1 plus x raised to the power of p, so f of 0 is 1. The first derivative is going to be p times 1 plus x raised to the power of p minus 1. And when you evaluate the derivative at 0, what you're going to get is equal to p. And finally, the last hint I'll give you is that the second derivative is p times p minus 1 times 1 plus x raised to the power of p minus 2. And the rest I think you can manage on your own. And after constructing the Maclaurin series, you should arrive at this formula or at this compact formula here. So I wish you massive luck with calculus in the future and mathematics in general. I hope this playlist was more than helpful, and I really hope to see you in more future videos and playlists. So, have a nice day and bye.